Welcome to the Final Wager's Guide to Game Theory. Today, we're going to be looking at zero-sum games. In a zero-sum game, one participant's gains are offset by losses from the other players. In other words, if you add up all of the winnings and all of the losses, they'll equal 0. One way to think about this is to say that no value is created or destroyed. To illustrate a zero-sum game, let's say there are 4 people playing poker. They each start with $25. If we add up the money on the table, we see that there is $100 total. Our players play a hand. Orange starts the betting at $2. Blue calls, purple folds, and green calls. So there's now $6 in the pot. Each of the 3 players in the hand has contributed $2, leaving each with $23. Orange bets first again. This time he comes out big, betting $10. Blue and green quickly fold. Orange has won the hand. There's $16 in the pot, so he adds that to the $13 in front of him, giving him a total of $29. We look at the totals for each player. When we add those together, we see there's $100 on the table. Exactly how we started. The term zero-sum comes from looking at the profit or loss for each player. Blue has lost $2, purple is even, green has lost $2, and orange is up $4. If we add those differences together, we get 0. The total gains of $4 are offset by the total losses, 2 players having lost $2 each. Let's return to our definition of zero-sum game. When analyzing a 2-player Jeopardy game, we'll assume a win is worth +1 and a loss is worth -1. We'll also assume, for the sake of simplicity, that no ties are allowed. Here's the situation we looked at in the Nash Equilibrium Guide. The leader has 20,000 and the trailer has 14,000. Each has 2 options from which to choose, a large wager and a small wager. The ranges here reflect the fact that a tie is not allowed. Let's work through the payoff matrix for this situation. The leader, represented by the rows, can wager either small, 0, or large, 8,001. The trailer, represented in the columns, can wager either small, 0, or large, all 14,000. We first look at what happens if they both wager 0. Each player will be either right or wrong. That means there are 4 combinations of how our 2 players can respond. Both are right, the leader is right and the trailer is wrong, the leader is wrong and the trailer is right, and both players are wrong. When both players wager 0, no matter how each responds, the leader will have 20,000 and the trailer will have 14,000. That means the leader will win in every case. We replace each score combination with the payoff matrix notation +1, -1. Remember, the leader is represented by the first number and the trailer by the second. Now we look at what happens when the leader wagers 0 and the trailer wagers 14,000. Remember our 4 combinations. The trailer will win if he gets it right and will lose if he gets it wrong, because no matter what, the leader will have 20,000. We replace the scores with the appropriate notation. We do the same for when the leader wagers 8,001 and the trailer wagers 0. If the leader gets it right, he'll win. But if he gets it wrong, he'll lose. Finally, we look at what happens when both players wager large. The only combination in which the trailer will win is when he gets it right and the leader gets it wrong. We replace these with +1 and -1 where appropriate. Now we've lighted this payoff matrix up like a Christmas tree, and we look at the intersection for each individual decision. Where both players wager small, the leader wins every time, so his total score is +4. The trailer's score is -4. They add up to 0. In the upper right-hand corner, where the leader wagers small and the trailer wagers big, our scores offset, 0, 0. The same is true where the leader wagers big and the trailer wagers small. And in the bottom right corner, where both go big, the leader wins 3 times and loses once, giving him a total of +2 and the trailer a total of -2. We can see that this will not have a Nash equilibrium that's immediately obvious to us. If we start at the bottom left corner, we'll see the leader can do better if he wagers 0 if he thinks the trailer will wager 0. And as we saw previously, we'll keep circling around the matrix with no end in sight. We can convert these payoffs to percentage possibilities as we did in the last segment. But this situation is still a zero-sum game, and as a result, has no readily apparent Nash equilibrium. But it does have one, and it involves a bit of randomness. We'll look at that next time, on The Final Wager.